大家好，歡迎大家翻嚟我哋嘅下半場嘅 Summit Conference。咁跟住落嚟咧，我哋係會邀請到 ARUP 嘅 Mr. Jeremy 去 present 佢嘅topics 嘅。And his topic is hydrogen development for buildings. Jeremy, it's your terms.
Hi, thanks for that.
Hi.
Yeah, I'll just turn on my camera real quick.
Yeah, it's okay.
All right. Well,
And
thanks for
you
having
will
me.
you will share your screen more.
Yeah, happy to share the screen. I've got the slides open if you need. Yep, I'll
Okay.
do it now.
Okay. Thank you.
All right, can you see my screen now? All right. So thanks for having me, everyone. Today I'm here to present a short piece of research that we did internally within ARUP. This was to look at the potential of using hydrogen for decarbonizing in the building sector for Hong Kong specifically. Now, a quick presentation about ARUP. So we are a global and multidisciplinary firm. We've been involved with infrastructure projects all over the world, including hydrogen projects, either as engineers, as planners, as consultants, or just as technical specialists. But we cover all kinds of services and types of fields like building services, structural engineering, MEP, sustainable design, as well as infrastructure. In East Asia, no, in Asia in general, we have about 15 offices spread around, but I am based here in Hong Kong, which is our hub office for the Asia region with about 1,500 employees here. Now, we have been involved in a lot of alternative fuel projects around the region. Um, and we've been very active specifically across East Asia and Southeast Asia as well. So, for instance, in Singapore, we've been involved with techno-economic studies or supply chain studies for the Singapore and UK government. And we just recently completed a project for a private investor in Singapore that was looking at decarbonizing CCGT turbines with alternative fuels like green hydrogen, but also blue ammonia, green ammonia, and other combinations of green fuels. But we also covered other parts of East Asia, such as Korea. We've also done Japan, which is not shown on this slide here. We've also covered countries like the Philippines and Australia as well, so beyond Asia as well. In Hong Kong, we've also been very active in hydrogen projects specifically. And this started really with the 2023 study that we did for the EMSD, in which they had started the feasibility of launching a hydrogen bus for Hong Kong. Now that is actually rolling in Kowloon, but we did the original drafting of the code of practice for EMSD. We also continued this with studies for the airport authority who looked at waste to hydrogen at their facilities. So we did the early concept design for that project. We looked at doing a risk assessment for the transport department at their depot in Qingyi. And just earlier, a few months ago, one of my colleagues delivered a study for a private client looking at liquid ammonia and hydrogen and the possibility of importing that to Hong Kong. Now, why look at hydrogen in the building sector for Hong Kong? Well, there's three really topics that are surrounding this. And the first is the geographical factors that we have around here in Hong Kong. So the main thing is that there is a large breadth of choice when it comes to hydrogen production projects in the Guangdong and GB area. So large hydrogen production, but also transmission projects that could feed into the Hong Kong demand. Hong Kong also benefits from its status as a global trading hub, which, if resorting to overseas trading, can be very beneficial for the Hong Kong context. And in terms of policy and regulation, the Hong Kong government has always pushed through with hydrogen as a means for decarbonization. And in fact, there's been very recently a consultation on an amendment to CAP 51, so the Gas Safety Ordinance, to incorporate hydrogen on the same level as town gas. But I think one of the most interesting factors about Hong Kong is the technical aspect, which is that the town gas distribution network already includes 50% hydrogen by volume, something that Dr. Kong from Town Gas already explained in the last series of webinars. And some of the technical factors outside of Hong Kong that are allowing this are mainly related to developing a viable global supply chain. Now, some of these look a bit old. There was already the liquid hydrogen delivery project back in 2022 by Suiso, and then some more demonstration projects in the Netherlands, in Korea, in the in North Africa. But I think one of the more recent developments that is very interesting, and that's not shown in this slide, is actually the memorandum of understanding between Marubeni and Envision in China to export green ammonia from Inner Mongolia to Japan. And that shows kind of a drive to international supply chains of green and blue hydrogen and ammonia. Now, to introduce this study very quickly, so we looked at this in 4 stages. We first developed a high-level concept design. So this was looking at how can we use hydrogen in a building using perhaps the town gas supply as direct supply of hydrogen. Then we did a brief regulatory review, drawing on our past experiences in consultancy studies here in Hong Kong. We looked at doing a decarbonization estimation, so essentially a well to gate decarbonization estimation, and then looked at different stakeholders that we could discuss this with, eventually target as a consultancy, and kind of carry this forward as a concept. Very quickly, because I'm sure Tom Gas has covered this already, but this is the original pilot project that was launched back in 2023. The pressure swing absorption system that was used back then was a rotary type pressure PSA. And very simply, it extracts the town hydrogen from the town gas pipeline and re-injects any sort of residual gas, which is separated from the hydrogen, back into the town gas network. To develop this concept design, we looked at a range of different commercial solutions, and there are many actually commercial solutions already on the market. Now, there are some like the refire systems, which can be very large from 1 to up to 3 megawatts in capacity. But when we're looking at the building scale, we wanted to keep it relatively small. And in consideration of the actual energy demand of typical buildings in Hong Kong, we wanted to limit this as much as possible. So we ended up settling on this system by EFOY here on the right, which is a 50 kilowatt system. There's no major reason for this, except from that it fit the right range that we were looking for at the time. It also has a built-in inverter system, which is very important because you don't want to have to install a separate inverter system, which would complicate the installation. So that's why we ended up picking up that system, but you could have just very well have picked up a Toyota system, a smaller refire unit, a Honda system, or a Ballard unit. Taking the concept of the town gas pilot a bit further and to expand it to meet the demand of a 50 kilowatt system, we essentially just expanded the town gas pilot and did a feasibility based on that. So we use the same exact components, so 2 rotary PSAs in our case to meet the hydrogen demand of the system, and multiple compressors, first to compress the hydrogen, but also to compress the residual gas that gets re-injected to a town gas network. And based on this, and using NFPA as a guideline for sizing and separation distances, we get a system that is about 100 square meters in size for a 50 kilowatt rated power system. We could have looked at other supply methods in this case. So for instance, you could consider bottle supply, which is probably the first port of call for most of these cases. And that makes a lot of sense if you're looking at backup power supply type of system. But if we're looking at in operation decarbonization over a long period of time, this becomes a bit more difficult because it implies frequent deliveries of bottles to site, perhaps pallets of 15, for instance. There are other types of systems like tube trailers, which would reduce the frequency of these deliveries, but in a high density urban environment like Hong Kong, we could imagine that would be quite difficult to deliver tube bottles to site on a regular basis. We didn't even look at the pipeline supply just because there is already a pipeline supply in the form of town gases distribution network. Forming a dedicated hydrogen pipeline network would just be too much of a capex investment for this type of solution. So knowing this, we looked at what would be the regulatory background based on our past studies in this kind of field. And to put it very simply, hydrogen is currently a dangerous good under CAP 295. Most of you probably know this already. there has been a consultation on moving the scope of hydrogen from CAP 295 to CAP 51, so under EMSD. And there's an ongoing, well, actually a completed consultation for this CAP 51, the Gas Safety Ordinance. And this has meant that there has been new codes of practices for hydrogen systems, new QRA requirements by MSD, new inspection requirements from competent persons. Now, the interesting thing here is that there is no code of practice on fuel cell power generation, although this is currently in the works, or as we understand it, is possibly going to come out in the next few years. And what we expect is that it would likely reference NFPA, but also probably GB standards. So we internally at ARUP often use NFPA as our standard, just because we have a lot of projects in the US as well. And this is what we based our study off of. To do a well-to-gate emissions estimation of the project, it gets quite complicated, in fact, just because you need to consider several factors, one being the carbon intensity of the town gas that you're extracting from the town gas distribution network. But you also need to consider the carbon intensity of the electricity used to power the pressure swing absorber and the compressors. And this means that your system is still somewhat dependent on the carbon emissions intensity of the power supply that you're using. So here on the right, you can see, for instance, that a system that is using CLP electricity would actually have a similar carbon intensity to just using CLP electricity directly to power your building on a kilogram CO2 per kilowatt hours basis. If you're connected to an HKE system, that's a bit different. At this point, actually using this PSA system is beneficial in terms of reducing carbon emissions compared to directly just using electricity from the HKE network. And the reason for this is obviously that the HKE network has a much higher carbon intensity when compared to the CLP emissions CLP system. This is all based on 2023 data, by the way, a quick disclaimer on that. So this is obviously going to change very quickly over time, and that's why I want to show in these next few slides. So to put all the sustainability targets of HKE and CLP on one page, we plotted this very quick graph here. We interpolated linearly between the different targets of HKE and CLP sustainability reports. But of course, with a caveat that in practice, linear decrease in carbon emissions per kilowatt hours is not realistic. It'd probably be in a stepwise fashion, perhaps as HKE closes down further coal power plants or CLP starts importing more power from Diabay nuclear power station. But anyway, I just wanted to communicate in this slide that overall, by 2050, we are expecting a carbon intensity of essentially zero, as most companies are looking for net zero carbon emissions of zero by 2050. And based on this, we can kind of estimate what would be the carbon emissions intensity of our PSA system over the coming years up to 2050. Now, looking at the HKE system, I did mention that if you're using, say, 2023 benchmark data, your system, the PSA, would have a lower carbon emissions intensity than if you use electricity directly from the HKE system. But the problem is that over time, this advantage decreases to about 2035, where in fact, you're just as well using electricity directly from the HKE system as power from your PSA system. So what I'm trying to communicate here is that over time, your benefit reduces up to 2035. With CLP connected systems, it's essentially equivalent throughout up until 2050. The PSA connected system performs just as well as if you were connected directly to the CLP power network, so there's no direct benefit in terms of decarbonization in this case. There's also the interesting case of if we were to compare this to town gas, and by that I mean if we were using just town gas and burning it on site, say for cooking or for hot water heating, using a PSA has no advantage compared to that. You're better off just burning town gas on site. Now, I just want to caveat all this by saying that we did not look at a hybrid system where you might use residual heat from the power from the fuel cell. There are commercial systems now that are coming on with this ability, which can actually increase your PSA energy efficiency, sorry, your fuel cell energy efficiency quite drastically. But we're not reflecting this here because we were trying to keep this as simple as possible for the sake of this early feasibility. Now, looking at what type of stakeholders you might want to approach for this kind of system, we basically focused on stakeholders that had a combination of high space availability and low energy use. So in terms of kilowatt hours per year per square meter of surface area, as well as simple forms of ownership. So can the owner of the building actually be the owner of the PSA system? Or do we need to introduce more complications like can it be owned by the tenant? Or do you need some sort of sharing agreement between the tenant and the owner of the building? We're trying to avoid these sort of complications when it comes to contractual agreements. Um, we're also looking at places where you can offer synergies with other applications. And this is something that already Town Gas, of course, has been looking at before with using hydrogen to power EV chargers, for example. So that's an example of a perfect synergy of a hydrogen extracting system with a transport network. And so based on that, we find that the most likely adopters of this kind of system would be warehouses and logistics centers, just because they have a very, very large surface area. So for instance, if you're a logistics operator like, say, Goodman, you might be interested in developing this kind of system either on your rooftop or at ground level. There's other stakeholders that might be interested in this. There's the HKIA, the airport, and large school campuses, so HKUST or Hong Kong Science Park, for instance. So yeah, I'm just outlining here the key building types we look at. These are firstly campuses. So this is perfectly in line with what Towngas is doing with the Hong Kong Science Park. There are possible synergies with EV charging, for example, but also just general decarbonization of building power supply. The airport offers a similar opportunity, and in fact, the airport has already expressed interest in using hydrogen to decarbonize their system, and they've also explored looking at using hydrogen for their ground fleet. So this could be another synergy of how to use this PSA system for decarbonization. Data centers are also an interesting case just because they have a very large and very stable energy demand. But what we find is that really in the grand scheme of things, the size of this PSA and fuel cell system would be so small compared to the actual demand of a data center that the impact would be minimal. And then, like I said, warehouses and depots are probably the most interesting types of stakeholders in terms of direct power decarbonization, just because, especially in the case of non-refrigerated warehouses, they don't have a high energy consumption in terms of kilowatt hours per square meter. So, sorry, the key takeaways I'd like everyone to come away from with this presentation, which admittedly is very short and full of caveats, is that Hong Kong is in a very good place for exploring hydrogen and the hydrogen supply chain, and possibly harnessing this to kind of decarbonizing both the power sector, but of course also, for instance, the transport sector, the construction sector, um, or the industrial sector. There are commercial solutions out there. I'm sure there's many people on this call that represent OEMs that are involved in this kind of system. Um, so these exist and they can be used in the case of the Hong Kong building sector decarbonization. Now, what we find, and this is from the comparison of the CLP and HK connected systems, was that the decarbonization effect could be minimal, especially in the case of a CLP connected system, if the CLP grid followed its sustainability targets. HK systems are a bit more beneficial. There's a bit more of a difference between power sourced from this PSA and fuel cell system as opposed to power directly sourced from the electricity network. And lastly, um, we identify the key stakeholders that might be most interested in developing these type of system, and these are typically warehouses, logistics centers, possibly data centers. There's also the side benefit that they might act as a backup power supply, although, like I said, the size of this fuel cell system might be quite small relative to the actual energy demand of a whole data center building. And then lastly, campuses where there can be synergies with mainly EV transport. And I think that's come under time by quite a bit. Um, hopefully that brings you back on schedule. Um, let me know if you have any questions. Happy to answer any sort of questions on this or point you towards the right people within ARUP if needed.
Okay, thank you, Jeremy. It's a very excellent presentations.
Thank
Thank
you.
you for you. Thank you. Thank you.